Next up on the stage, we've got Olivia Gallucci, who is a senior security engineer at Secrecy.
Yeah.
Okay. Just wait. I'm sure I will go ahead and botch something with my tongue yet. She's also a personal trainer. She's been around for a while. She's spoken at many places. How many people here have MacBooks?
Yay!
How many people wish they understood what was inside a MacBook?
Yay!
How many people here want Shecky to just shut up and get on with it all? All right, here's Olivia for you with the whole thing on unlocking macOS internals.
Hi. All right, hopefully everyone can hear me. So hi, everyone. Thank you so much for being here. My name is Olivia Gallucci, and I'm a security engineer at Secrecy, which is a consulting MDR and research firm in Germany. And today I'm going to walk you guys through the foundations of macOS internals and how to start exploiting them using Apple's open source code. So what are macOS internals? macOS internals are the underlying components that make the system work. The XNU kernel, process and memory management, system libraries, syscalls, device drivers, basically everything that runs under the graphical user interface. It's the difference between what you click and what's actually happening when you click something. macOS internals matter in so many contexts like security research, performance tuning, or debugging weird system behavior. It lets you analyze vulnerabilities, understand potential undocumented features, and even patch behaviors. And there's a bonus for iOS researchers, which is that iOS shares its core with macOS. Now, I want to address the elephant in the room, which is Apple's secrecy. And its secrecy is problematic for a number of reasons, but it's a myth that 100% of Apple is closed source. A large chunk of macOS and iOS is actually open source. Apple publishes the XNU kernel, system libraries like libc and libdispatch, daemons like launchd, and various other things. Anyone can go online and read the code that runs on a Mac or iPhone. Of course, Apple doesn't release everything. Some frameworks like Core Foundation and UIKit are closed, but what is public is incredibly useful, and knowing how to work around those gaps is really helpful in internals research. Now, let's explore the intersection between computer architecture and Apple's open source code. To understand Apple's operating system, we've got to talk about Darwin. Darwin is Apple's open source Unix-like operating system. It's the foundation for both macOS and iOS. And at the heart of Darwin is the XNU kernel, short for X is not Unix. It's a hybrid of the Mac microkernel and BSD. Mac handles task scheduling, memory, and interprocess communication, or IPC. BSD adds the POSIX APIs, networking, and file systems. And IOKit, which is written in C++, manages the hardware drivers. There's some other things in this mix too, but we're not really going to get into those. And so when Apple builds macOS and iOS, they're layering proprietary features like the GUI and frameworks on top of Darwin and XNU. So yes, macOS and iOS literally run on the same base OS. Here's just a cool diagram of how Ubuntu and macOS compare. It doesn't really have to do with much other than I thought that people might find it cool. So let's explore this shared foundation. Here is a table comparing some system daemons and services. You'll notice that launchd, mDNS responder, the preferences daemon, PowerD, and others run on both platforms. Sometimes they're even identical. Because of this, vulnerabilities found in macOS daemons can also exist in iOS too. And as you can guess, it's an advantage for researchers. You can debug and reverse macOS binaries, which are easier to work with in my opinion, and then apply that knowledge directly to iOS. Another important note is that in general, iOS is considered to have more restrictions because it has stricter sandboxing, entitlements, and application isolation. But underneath those constraints, the code is often the same. So what is actually available? Apple publishes a range of open source components like the XNU kernel, core libraries like libc, libsystem, libdispatch, and some other daemons like launchd. If you go onto their open source page, you'll notice that it's like over 400 repositories online. These are all downloadable, inspectable, and sometimes even buildable. But they don't publish everything. Missing or partially available components include Core Foundation, CF Network, launched D in recent releases, iOS-specific drivers, the full dynamic linker, and their crypto library, which is known as Core Crypto, and it even has like legal protections like a 90-day and then delete policy, which you can find online. Additionally, its source drops are often incomplete or outdated. You'll see headers referencing files that don't exist or tarballs with build instructions completely missing. So while Apple's open source code is a goldmine, I think it's important to approach it knowing you'll hit some walls. The big idea here is that macOS and iOS share the same core. Apple open sources more than most people think, but not everything, and navigating this code is essential for internals research. Now we'll talk about how to actually find and use this open source code. So Apple's open source a surprising amount of code, as I've already stated, but the company, from an outsider's perspective, is also kind of redacted, or explicitly redacted, and has really moved around a lot of these resources, and as a result, depending on how you're going about accessing this code, it can be really difficult. For example, a tutorial written 4 years ago might include links to exclusively 404s if that tutorial links to Apple's downloads or source dumps before 2024. So then, where do you find this code? Historically, Apple published their source code as gzipped tarballs on its open source website. These archives were organized by macOS version, so things like XNU 8792.4.9.tar.gz, and so on, right? And that worked until it didn't. In March of 2024, Apple began retiring these direct downloads. Now the primary home is its GitHub organization called Apple OSS Distributions. Each component now has its own repository tagged by version. So instead of downloading from Apple's website, you're grabbing release zips or browsing repos on GitHub. Now, how do I navigate GitHub? Well, as always, each repository follows a basic format, starting with a name like XNU, libdispatch, or libc, and then a set of tags like XNU 8792.41.9, which maps to a specific OS version, and then a release field, again, if you're lucky, that tells you what macOS or iOS version it matches. But here's the catch. Apple just doesn't always explain these mappings clearly. And this is extremely important because you can't often explore things properly if you're not using the version of Xcode used to develop that specific component. For example, XNU version 8792.41.9 corresponds to macOS 13.4. But Apple doesn't just tell you that. You have to infer it by checking the release pages or using community-maintained lists like Wikipedia's version history. Unfortunately, there's many challenges with Apple's open source releases, and I'll cover the three main ones here. First is delays. Code usually appears weeks or months, maybe even years after the OS ships. There's no warning, no schedule, just coming soon. So, like sometimes even 6+ months, the release pages will still have a coming soon notice. And then next is incompleteness. Some tarballs are missing files, headers reference code that just is not there, and then entire components like Core Foundation or newer Launch D builds are MIA. And then lastly is tag confusion. One second. So tags like, XNU 8796.121.2 mean nothing unless you know how to decode them. And that's why learning how to use Git tags, learning, general project structures, and knowing how to use Git and GitHub in general is really useful in this process. So I want to go into a few more tips and tricks I use. First, I check the release field if it's available in the repository metadata, and if it ever says something explicitly, or if you can find something explicitly like macOS 13.4, use that, it's usually accurate. I also use Apple's distribution manifest to cross-reference components per release. Lastly, I look for clues in the binaries themselves, like version strings or source file names via strings or what programs, to figure out which project a binary might have came from. And what I've learned is that finding the source code is doable but messy. And again, Apple doesn't make this easy, but with GitHub, a few sleuthing tricks and some trial and error, you can usually track down the source for many major system components, with the caveat being it might be a much older version of that component. So yeah, now I will show you how I actually use the source code, especially when it's incomplete, to do reversing insecurity research. Okay, there we go. Specifically, we will be looking at how to use Apple's open source code to examine system binaries. Even though the code is often incomplete, it can still guide your research. The key is to treat it like a map. You might not have the full territory, but the landmarks are real. And what I do, and what many other security researchers do, is use Apple's open source code as a reference while working with the binaries. You take a binary like launched, syslogd, a kernel extension, or whatever you want, and use the available source code to do various things. For example, I might try to match known functions. This helps identify familiar code in binaries, making it easier to understand behavior and verify functionality against Apple's open source implementations. I might also try to annotate call patterns, which reveal how functions interact and in what sequence, allowing me to infer program logic and detect deviations from expected behavior. Lastly, I might try to reverse unknown logic. Although difficult, attempts at this enable me to uncover the purpose and/or vulnerabilities of software that lacks source code, using structure and context to reconstruct what it does. Essentially, even when symbol names are skipped, you can use structure, string constants, or known syscall usage to map back to open source code. And here are 4 tools I use to do this, and if you've already been in the reversing space, these tools probably aren't new to you. Of course, there's strings, which dumps human-readable strings. This sometimes includes debug messages, file paths, and format strings. Then there is what, which extracts version and project information from binaries. There is NM, which lists symbol names, especially in unstripped binaries or frameworks. There is also class dump, which extracts Objective-C class and method definitions, and it's great for finding things like interface information. And through using all these tools, I can figure out which open source package a binary might have came from, or have like some sort of like ancestry in, or what APIs it's using, even if I don't have the source code or the exact version. And then after this, I'm usually at a point where I want to go a bit deeper. Here, I would generally use some sort of binary diffing, which is the process of comparing 2 compiled binaries, typically before and after a patch, to identify changes, which helps pinpoint patches or changes and vulnerabilities within that source code. Tools like BinDiff and Diaphora, the person who made it says like Diaphora, but I'm going to call it Diaphora. They let me compare 2 binaries, again, like before and after a patch, and maybe spot those changed functions. To give a theoretical example, if Apple silently fixes a vulnerability in syslogd, I could try to diff the old and new binaries and immediately see which function changed. Then I could grep the open source code for that function, reconstruct the patch logic, and then reverse the vulnerability from there. If you prefer Ghidra, the kernel cache plugin lets you load XNU function signatures into the kernel cache. I really like this plugin, and I did a workshop on it once, and it was great. So yeah, it auto-labels all like the known kernel functions using headers, and this is a really big time saver. And in the academic sense, we can actually look at the example I just described. In 2016, a researcher named OSX Reverser used Diaphora to diff syslogd from macOS 10.11.2 and 10.11.3. Only one function had changed. And as you can see in the code on screen, in syslogd's add lockdown session function, the call to realloc_f plus 4 was changed to realloc_f times 4 plus 4, which was to allocate enough space for each session and prevent a heap overflow. All other functions remained identical, same thing with the call graphs. And inside this, he found a string that read add lockdown session realloc failed, and this led him to the vulnerable code within Apple's open source syslogd. And this kind of surgical diffing is how some vulnerabilities are reversed after a patch. This is especially important because security fixes often need to be applied across multiple files and locations. For instance, suppose you patch identical code in files 1 and 2 on macOS, but neglect to update files 4 and 5. which is very common because these operating systems that just have tons and tons of files. And in that case, the unpatched files 4 and 5 still contain the known vulnerability, leaving your system at risk. It's also worth noting that updates can be platform specific. If the iOS versions of file 1 is patched, but its macOS equivalent is not, macOS remains vulnerable, unless, again, there's other like security protections in place, which oftentimes there is. The same actually goes for kernel extensions. By diffing KX across versions, researchers have found changes to external method tables surfacing newer patched entry points in IOKit drivers. Thus, even partial source is powerful. Combine it with binary analysis and you can reverse Apple's systems with surprising accuracy. And here you can see you're not really flying blind, you're flying with half of a map, a flashlight, and some really good tools. So, you might be wondering, can I just like build macOS? I too get ambitious with my findings, and I'm like, time to compile macOS from scratch. I have since learned that compiling these components yourself, or at least for me, is only sometimes possible and almost always painful. I'm sitting there with Apple source code downloaded, and I'm ready to compile like whatever I've downloaded. And after hours of frustration and dreams of achieving some new like mental research PR, I embrace this truth of you, or maybe just me, can't just build macOS. Not completely, not cleanly, and definitely not without frustration. So what makes compilation hard? It's hard really because of 3 main reasons. First is incomplete source code. Apple regularly omits proprietary or device-specific code. For example, there's instances of all ARM-specific assembly being stripped from iOS XNU, missing power management subsystems like CPM, and to this date, some important drivers and frameworks have never and probably will never be published. Second are environment mismatches. Apple builds, like all companies, with their own internal tools and exact Xcode versions. If you're off even slightly, you'll hit missing headers, undefined macros, compiler flag mismatches, and linker errors. And lastly is sparse documentation. Although I doubt this is a new problem for anyone who's into, Apple security research, right? You probably won't even get build instructions. There's community guides, but most of it is trial and error. And at least for me, I always end up having this constant feeling of excitement and confusion. I'll spend hours resolving dependencies that Apple never documented and patching quirks like what you see on screen. And this isn't a joke, by the way. This is a real fix from a Mojave XNU build. So if you can't fully build the OS, why even try? Well, you still get a huge value from reading the build scripts and headers, tracing the structure and the logic, compiling parts like libdispatch, and testing patches in controlled environments. And even if said patches are kind of janked on some OS versions from 10 years ago. I think of the build as a reference model, not a product. One tip I have is to use the iOS simulator on Xcode, which allows me to obtain working binaries with symbols and less cache extraction pain. It includes standalone dilib frameworks, works with public symbols, ARM64 slices, and versions very similar to real iOS like version/device usage. And you can load these into IDA or Ghidra and reverse cleanly, and you don't require any sort of jailbroken device. It's an amazing shortcut for when source code is missing, but you still want visibility into system behavior. And all this is to say that compiling Apple's open source software is hard and incomplete, but worth it. Every build error, in my experience, teaches me or has taught me something about how macOS is stitched together. I try to use this process as a learning tool, not a goal. And all of that said, what do we learn? macOS and iOS both run on Darwin. It's Apple's open source Unix-like foundation. That means that what you learn on one usually applies to the other and vice versa. They share the same XNU kernel. Many system daemons and tools are cross-platform, and much of the good stuff, like launchd, libc, etc., is available in source form. Apple might be secretive, but its open source code is one of your best research tools. You just have to know how to use it. So then, what's like the strategy here, right? First, use the open source code that Apple does release, study the headers, read the build scripts, and match symbols and functions and whatnot. Second, when things are missing, try to reverse those binaries. use tools like strings, NM, class dump, BinDiff, Ghidra, combine static and dynamic analysis, diff updates, follow any sort of breadcrumbs you can find. And then, whether it's macOS or iOS, the internals are usually more open than you think, and even the gaps are reverse engineerable with the right tools. There's also whole communities built to talk about this stuff online, which helps a lot too. And so, right here, this talk hopefully should give you a starting point for everything you need to start hacking these machines. And as you can see, it's not really just about compiling code or reading docs. It's about building the confidence to explore Apple's GitHub repositories or some random dilib you found. And if you're curious, methodological, and really just persistent, you can really do amazing work in the security research space. And in terms of the content of this presentation, thank you so much for your time and happy reversing. But I have some terms of where you can go after this. So 1, all citations and resources are included in the footer of these slides and images and whatnot. And if you want to get involved with the macOS community IRL, there's 2 amazing conferences, Objective by the Sea and Objective for the We. This one's going to be in London and that one's going to be in Spain this year. I've both benefited a lot from these conferences and I absolutely love them. And full disclosure, I have strong ties to both of them. There's also Mac DevOps conference, which is in Vancouver. I met the organizers last week. They're great. And then if you're interested in my other work, I have a couple presentations coming up next week on macOS internals. And yeah, all my written work is available online. And I recently wrote a blog post on macOS internals for detection engineers if you're someone who focuses more on the defensive side of things. And yeah, thank you so much for your time. I hope you all enjoyed my presentation. And if there's time for questions, cool. Hi.
So between the x86 and ARM64 binaries, which you prefer?
ARM, because I recently graduated from college, so the amount of time that I've been competent in this space has been limited. And the time that I have been competent in this space, it has all been ARM. Okay. So ARM.
Okay. And the second question. So you mentioned the strict binaries and unstrict binaries. Do we have access to the debug versions of whatever libraries they compile with the unstrict binaries? Because I would assume everything is released strict.
Yeah. So part of it. So there's whole tutorials about how you can do this in an organized fashion online, but usually there's some pre-processing in place that you need to do to get the unstripped binaries, because they're not always available. I think Chabal Fitzel actually was the person who published a piece on this. It was either Chabal Fitzel or also OSX Reverser. One of them was hey, here's how you can organize these things so that you can actually understand what you're looking at. And the same thing with the tools as well. One of them actually had a full tutorial on how you can actually get usable information from the binaries.
Okay, so there's a service from Apple that you can download them somehow?
Oh, okay. So you mean okay, yes. There's a website, and then there's also the GitHub. You should be able to get them, some of them from both, and they're also organized by system component as well.
Because back in the days, in Windows times, you can download PDBs, unstripped, basically debug binaries from Windows. And I'm curious what's available for the Mac.
So I think I had a little GIF going through their website, but if you go to I think it's open source. Don't quote me on this. Just search open source Apple, and then you'll find that website. But on that website, you'll go into developer tools on the OS page, and there should be ones for Mac, iOS, I think iPad. And then there's a developer tools section.
Thank you.
So that's where I would go. Any more questions?
Is there any enforcement for any of those repos that Apple requires you to have for 90 days?
Oh, so the core crypto one, I know for a fact, yeah, but I think it's the usage of it itself, because you have to like partner with them in a way, like you have to get like signed things from them. And also there's oh yes, can I take a selfie with everyone?
Sure.
Yes.
Okay, I got like 6. But yeah, sorry, what was your question? Yeah. Okay, yeah, okay, cool. But yeah, some of them do have special policies, but it's usually not the open source ones, because the license is always attached to that, so that would be the policy. Anything with like special things, you usually have to get through an Apple portal that will make you like sign in and whatnot. I think I'm done. Yeah.